All right, let's talk about Monday's class. So that way you can choose to just watch this. Here's the stuff I'm supposed to talk about. And the big thing I want to get to is derivatives of inverse functions, even though we're going to skip the derivative of a general inverse function. But inverse functions are things like a natural log or arcsine or arctan and stuff like that. Technically, the square root is also an inverse function. So I've already told you in class that if f of x is 3 to the x, then f prime of x is the natural log of 3 times 3 to the x. Okay, but why is this the case? And the answer really has to do with the chain rule. So if we use this function and I hit it with a natural log of, and then f of x, well, that's equal to the natural log of 3 to the x, and that's equal to just x. Well, times natural log of 3. So the natural log of my function, so this is function composition, is equal to x times natural log of 3. And these are spot on equal. That's why we use equal sign in mathematics. And if two things are equal and you do the same thing to each side, they're still equal. So I'm going to take the derivative of each side, because we're in calculus now, and that's what we do. d dx, d dx. Okay, so on this side, the derivative, we have to use the chain rule. So natural log says, 1 over times, and then I have derivative of f is equal to, and over here, this is just x times a constant. This is a line whose slope is natural log of 3, so the slope lives, I get natural log 3. And if I move over the f of x, I have f prime of x is equal to natural log of 3 times the original function f of x, which really says f prime of x is equal to natural log of 3 times, okay, f of x is 3 to the x, so 3 to the x. And we already knew that, right? I already told you that. But really the chain rule is how you find out more advanced derivatives. And in fact, so the power rule, when I wrote x to the n becomes n x to the n minus 1, this is stuff where we could directly compute it in class. If I want to take the derivative and I had x squared, then this is the limit as h goes to 0 of x plus h squared. But you get what I'm saying. We could do this, but what was a lot harder is if I had to do the derivative of x to the, say, 1/7. And now this is the limit as h goes to 0 of x plus h to the 1/7 power minus x to the 1/7 power over h. That's much harder. And it turns out, well, if you're comfortable with the power rule being true when you have integer powers, and specifically just even positive integer powers, then we can figure out the reciprocals because they're inverse functions. The 7th root is the inverse of x to the 7. They undo each other. So here's what I'm going to do. I'm going to let f of x be x to the 7. And now if I take the, oh wait, no, that's not what, I'm going to flip it, sorry. I'm going to let g of x be the 7th root of x, which we can also write as x to the 1/7. And it's true that if I plug g into f, I get x, and if I plug f into g, I get x. They just undo each other. They are inverse functions. That's what it means to be inverse functions. When you compose them, you don't change the input. The input just goes on to be the output. So let's say we didn't know what g prime of x was supposed to be. What is this supposed to be? Well, we can say, well, f of g of x, so let's go back over here. Here's f and here's g, and if I put them together, I get x. So f of g of x is x, and in fact I could just write out what this really is. This is the 7th power of g of x is x. And now, let me give myself a little bit more room. I'm going to take the derivative of both sides. Derivative. And on the left-hand side, I have to use the chain rule. So the 7 comes down. I have g of x to the 6 times g prime of x equals, and on the right-hand side, it's just the derivative of x, which is 1. And now I solve for the thing that I was curious about, which is g prime of x. And I have 1/7 g of x to the 6th power, to the negative 6th power, I'm sorry, because I divide it. And now let's plug in what g of x is. This is 1/7, and then g of x was x to the 1/7 power, and that's being raised to the 6. This is 1/7, and I have x to the 6/7, which is exactly what the power rule says if I started with x to the 1/7, and I take a derivative. I have 1/7 x to the 1 minus 1, oh, flip it, Anthony, flip it, x to the 1/7 minus 1, which is, well, 1/7 x to the 6/7, because you'll have a negative 6/7 power. So, really, even though we only computed the derivative explicitly for x squared, and in some courses we do x cubed, it's really easy to see the power rule being true when you have a positive integer power, when you have, x to the 7 and stuff like that. That's honestly, it's because it's really easy to expand stuff like x plus h to a positive integer power. Maybe it's 5 or 7 or 15, who cares? This is really easy to do. It's much harder to think about x plus 8 to like a square root, x plus h, sorry, and then have a square root power. But even though we can do this easily, and then we can compute the derivative by the definition for small positive integer powers, I then quickly jumped and I said, oh, but here's the power rule, and it works for any number. And that was me just letting you guys use more machinery than we had at that time. When in reality, we only had it for positive integer powers. If those little details don't make sense, it's not too big of a deal. But the point is, if you know the derivative of some things, so like we know the derivative of x squared is 2x, then suddenly derivatives of things that were more complicated, such as square root x, we can figure out because these are inverse functions. And so I'll give this a costume and I'll call it g of x. And if I have g of x and I square it, I get x. And now if I take the derivative of both sides, that says 2 times g of x times g prime of x equals 1. And now I move everything over to have g prime of x is equal to 1/2 root x, which is 1/2 g of x. So you can find the derivative of harder functions by using this technique where you compose them with something that makes it easier. Let's try this with some trig stuff. So arc sine of x. This is the inverse function of sine. Let's do a quick little trig thing. If you have an angle, then sine of that angle will spit out a ratio, right? It's opposite over hypotenuse. Arc sine, you start with a ratio, and it tells you an angle that gives you that ratio. So here I'd say sine theta is O/h. Here I could say like arc sine x equals theta, and then the question is, what's the corresponding picture? Over here I have this picture of a triangle. How do I draw a triangle here? And okay, I want a right triangle, which I really should emphasize this is the right triangle. And it needs to tell me the angle, which is going to be theta. Okay, it's going to be theta. And what this is trying to say, well, okay, inverse functions make sense when you write them down the inverse way. What I mean is if I take the sine of both sides, sine of arc sine of x, these should be inverses, so they undo each other, you just get x. But on the flip side, I could write this as sine of theta, because arc sine of x equals theta. So I'm using substitution here. And so this lets you know, okay, sine of theta is equal to x, which means this is x over 1 is a way to think of it. We need to get a ratio of x. And we're going to end up using, this is called a reference triangle. Reference triangle. A lot. Okay. So, arc sine, you give it a ratio, like say arc sine of 1/2. And arc sine will say, oh, well, the angle in radians, that'll give you 1/2 in sine, is pi over 6. And so this statement here is the same as the statement sine of pi over 6 equals 1/2. Right? It's just a little more confusing for the same reason division is more confusing than multiplication. This is the inverse operation. So division is the inverse operation of multiplication, and it's more confusing. But, 8 divided by 4 equals 2 is the same as saying 8 equals 2 times 4. Same idea, it's just now it's with angles and ratios and stuff. Okay, so we have some function, f of x equals, not sine x, cool it Anthony, it equals arc sine x. And if I take sine of that, I just get x, because these are inverse functions. It's just like taking the natural log of e to the x gives you x. It's like taking the 1/2 of 2 times x gives you x. It's like taking the square of the square root gives you x, right? The sine of the arc sine just gives you x. And now I take the derivative of both sides. So the derivative on the left requires the chain rule. So I have cosine of, keep the inside the same, times the derivative of the inside equals, and now I take the derivative right hand side, which is 1. And now I solve for the thing of interest. So f prime of x is equal to 1 over cosine f of x, which is to say it's 1 over cosine of arc sine of x. And this is where that reference triangle comes into play again. Make it a little better. I want a 90-degree angle. And this was x and 1 and theta. And this is our reference triangle for the statement arc sine x, which you could think of as, I lost my pen, as x over 1, right, opposite over hypotenuse, is equal to theta. So arc sine of x is the angle. We're referencing this angle. And what's in here is cosine of that angle. Cosine is adjacent over hypotenuse. So we should figure out what this edge is. And so we have Pythagorean theorem, which is a squared plus b squared equals c squared, where we have a right triangle CAB. And that's what we use. So it turns out this is the square root of 1 minus x squared. So cosine of theta is the square root of 1 minus x squared over 1. And theta is arc sine of x. So cosine of arc sine of x is the square root of 1 minus x squared. So this is 1 over the square root of 1 minus x squared. Okay, now we have something. If f of x is arc sine of x, then f prime of x is 1 over 1 minus, I'm sorry, the square root. You see what I mean. 1 over the square root of 1 minus x squared. Let's try this again. We could have arc tangent of x equals theta. So what's a reference triangle for this? Tangent is opposite over adjacent, and this ratio should be x. And then arctangent will tell you the angle that gives you the ratio. So the easiest way to make this ratio x is you just let this side equal x and this side equal 1. So I'm just going to label them accordingly. I have x and 1. And that means the hypotenuse is the square root of 1 plus x squared. All right, well, tangent of arctangent of x is x. And now I take the derivative of both sides. But, well, yeah, okay, screw it. I take the derivative of both sides. So the derivative of tangent, if you work it out, you get secant squared. So we have secant squared of, and you leave the inside the same, arctan x times the thing we're trying to solve, which is the derivative of arctan x, equals, now I take the derivative of the right, I get 1. So again, this is the thing we're trying to solve for. We have this function arctan x, and we're trying to take its derivative. And okay, so I could write, and it's a true statement, the derivative of arctan x is 1 over cosine squared arctan x. And in case I lost you there, secant squared of anything is the same as 1 over cosine squared of that argument of anything. Or yeah, use this tablet so I can write better. Okay. Because secant is just 1 over cosine. That's how it's defined. Okay, so we need to figure out what is cosine of arctangent of x. So we go back to our reference triangle. So cosine of arctan x is the same as cosine theta in this reference triangle. And cosine theta is 1 over the square root of 1 plus x squared. So if I square that, square it, I have 1 over 1 plus x squared. Do I just have, no, wait, cosine is, why does this make me nervous? 1 over 1 plus x squared. And I would get 1 plus x squared, but I feel like I'm supposed to get actually 1 over that. Cosine is adjacent over hypotenuse. We got this from here. Oh no, I think this is okay. Let's see.